about audio, mainly about the audio AES67 and IPMX and how these things finally come together. Just a quick overview. I'll give a very quick and brief overview of AES67, SMPTE2110 and NMOS. Quick introduction, because you've all have heard this about IPMX, and then the more important parts, the timing models of IPMX, and how what that does mean for the interoperability between IPMX and AES67 and 2110. Again, my focus is on audio, but most of this can also be translated into the video side of things, of course. So, AES67, what was the original goal of AES67? Well, we had a number of disparate audio over IP systems which cannot talk to each other. And the idea was, can we achieve interoperability between them on the basis of IP? So they are all based on IP, these solutions like Hildebrand, Livewire, Ravenna, Dante, Wheatnet. There are probably a few more out there. They cannot talk to each other except, running audio lines. So except Livewire and Ravenna did work out in 2012 already how to talk to each other. But the idea was, if we define something which we now know is called AES67, which is supported by all of these different solutions, then we can exchange audio directly on the IP layer. So what is AES67? It's an interoperability standard. It's not a new standard, yet another standard. It's an interoperability standard, which is using existing protocols based on trusted IT standards, and that is designed to run on existing networks. So finally in 2013, right at IBC, so that is 11 years ago, AES67 saw the light of the day, and just in order to quickly understand what we are talking about later on, is every standard, every definition has functional blocks like synchronization, media, clock transport, and so on. And AES67 defined a mandatory minimal functional set or protocol set for each of these blocks to finally assemble something like AES67. So all the IP solutions needed to support these minimum functional requirements in order to achieve interoperability among solutions like Dante and Ravenna. And what we deliberately left off was discovery, because there were already existing schemes out there, and we could envision that other standards would come up, and so we didn't want to force any discovery scheme with the AES67 interoperability. Focus for the interoperability with what I'm talking about later with the IPMX is, of course, again, the synchronization and the media clocking, and parts of the discovery also coming into game when we talk IPMX. So if you want to learn more about AES67, just talk to me after the boat tour, or just look it up yourself on the AES67 standards page that I see. So SMPTE2110. Very quickly, it's basically very similar to AES67, except that it adds video to the game and metadata in terms of the ancillary metadata and everything. So basically, it's the same stuff AES has done for audio. If you look on at the IP side of distribution based on IP for video, we had the 2022 standard already in place, but 2022 is basically the full complex SDI signal encapsulated in IP, and that is being distributed onto networks. That is not very usable for production work, because everything is encapsulated. If an audio console just needs to access audio, well, it had to unpack the whole SDI, the whole 2022 packet, and then just extract the audio. This de-embedding thing, right? So, and that's why we have this an essence-based approach of 2110, where we have audio, video, and metadata, and whatever we need as individual essence streams on the network. And that is the ideal approach for production environments, and everything basically is held together synchronization-wise through PTP. We'll come to that in a second. This is just a picture highlighting the differences between the existing 2022-6 standard at that time. We have a complete SDI signal where everything is in one stream, in one flow, so every packet contains audio. Well, not every packet, but every essence number of packets actually for video, but they are all contained in the very same flow. And if an audio console only wants to work with audio, it has to receive the whole IP signal, de-embed the audio, re-embed it into a video and everything. And in contrast, 2110, we have these individual essence flows on the network, and the audio console only needs to register to the audio stream. So the audio flow process the audio flow and put a new audio flow onto the network. That's the basic difference between the already existing 2022 and the then released, and then with then I mean 2017. That's the year when 10 had been released by SMPTE. So just as a quick overview, there are lots of different standard documents describing different things like system timing, all kinds of video-related stuff. We have two important standards based related to audio, PCM audio and AS3 audio transport. Just recently we released the -41 standard, which is the fast metadata exchange standard, and I just can encourage anyone who is interested in the metadata thing, just come visit us at the Ravenna booth, because Dolby, Jünger and Bridge Technologies are showing a real use case which has been used already at the Olympic Games this year for metadata transport, SADM metadata transport based on -41 as a real use case, and we have that up and running at the Ravenna booth for demonstration. But now we are turning to the audio side of things and the system timing, in particular to the linear audio, which is defined in -30. So what does -30 specify? Basically, how uncompressed linear audio, PCM audio, is being transported. And essentially, we can say it's just the same as AES67. It adds a few little things here and there, but basically the two schemes are mostly compatible. One exception is that 2110-30 defines further conformance levels. AES67 only talks about 1 millisecond packet time, and that is conformance level A, versus B and C go down to 125 microseconds. That's an option for AES67. It's also option for 2110. But they are clearly defined if you want to have shorter packet time. So that's basically what we're talking about, and that is also becoming important for IPMX now. If you want to learn more about 2110, again, just talk to me or turn to the 2110 FAQ webpage or download the standards to read them by yourself. Well, usually those fully working systems cannot be built on just 2110 or AES67 alone, so we need more for a network system. Discovering resources, establishing connection, sort of these things are partly covered by Ravenna, Danta, Livewire and others. They are not covered by AES67 2110, as I highlighted earlier. Discovery was not part of the definition. So other things need to come into game, and that's, Jeremy already mentioned that. That's the NMOS suite of specifications, or specification documents hosted or driven by AMBA, the Advanced Media Workflow Association. And so NMOS is designed to accompany any AES67 or 2110 transport or media infrastructure themed to provide, discovery, connection management, control, and other things. And it's becoming a very important factor in the IPMX kind of thing. So just an easy diagram. We have all the transport layer stuff, which is covered by AES67, 2110. And then NMOS adds things like discovery, registration, connection management, audio, channel shuffling, and there's much more. Which is being worked on within NMOS or has already been defined, and it's very useful and important for this. So what is IPMX then? IPMX is an initiative by AIMS, and it's called the IP Media Experience. IP Media Experience, right? And basically, again, like the whole AIMS initiative for the other IP standards, it defines a common set of standards-based protocols which foster the interoperability for the Pro AV industry. Now, 2110, AES67 have all been designed with the ideas of mostly the broadcast side of things in mind, and now IPMX is targeting the Pro AV, the commercial audio, signage, everything you have seen, in the Eurovision, for example. Besides audio, it also incorporates other things like compressed audio video stuff, various video formats, HDC copy protection is an important part of the game, and of course discovery, registration, I/O stuff. And also they were looking at enhanced or relaxed timing, because the strict timing requirements set forth in 2110 for the broadcast use cases may not be required in most of the Pro AV use cases. So the goal of IPMX basically is simple deployment on networks, on IP deployment on networks for the Pro AV use cases. IPMX started with the existing standards, 2110, NMOS, but more functionality was needed. essentials of what you have these days at HDMI, and all these existing and new ingredients together build the IPMX suite of standards, basically. That's the idea of IPMX. IPMX itself, the technical parts are mostly driven by the Video Services Forum. They are producing the VSF technical recommendations, and the whole suite of TR10, again, you can see lots of documents here, is basically defining the IPMX standard. And other things are driven inside NMOS working groups. So particularly the edit data information, HTTP stuff, and more is all being covered by various NMOS groups and NMOS documents. Some of them are available, most of them are still in the works, are being worked on at the moment. All this together comes into IPMX. And just a very, very brief view, don't want to bore you with technical details at this particular point. That's the infrastructure and the physical layer. Then we have the existing standards like 2110, AES67. We have the various TR10 definitions which run on the technical infrastructure. We need additional functionalities, USB, GPI, and so on. Everything what is needed, typically needed in Pro AV use cases. Things which come with NMOS, and NMOS also will stretch out into covering some sorts of these GPIO, not GPIO, these control and IO stuff things. And then on top is a layer where you have what we call this application layer, but there's where we have control, we have authorization, access, and all these kind of things. And all this is, just sort of a high-level view of what IPMX basically can see as being built off. Now, we come to the important part of what I was talking about the clocking and synchronization, because that is what is really important, especially when you look at the audio side of things. IPMX defines basically 3 different operating modes. I call them operating modes. We could call them streaming modes. It's exchangeable basically at this point in time. First of all, because IPMX is based on AES67 and 2110, it incorporates what we call the fully synchronous operation. That is what is defined by AES67 and 2110, where all streams on the network are working on the very same common reference clock, and so they are working in fully synchronized way. That's basically what AES67 and 2110 are about, and IPMX thrives to be based on this, so that's one of the modes IPMX needs to support. Then we have an asynchronous operation mode. Well, most of the Pro AV use cases do not need the full synchronous operation. In most cases, it's fully sufficient if you have a signal which is running on its own media clock, you throw it into the network, it's being received by a receiver somewhere, and it doesn't matter if it's really synchronous, sample accurately synchronous to anything, like an HDMI input signal, you throw it onto the network, you play it out on a TV screen somewhere, cinema, foyer, or something like that, right? However, there's in this mode, there still is a common reference clock available, so you can relate the asynchronous input data time-wise to a common reference clock, to time, so that the receiver has the chance to play out any input signal at a certain given time. Right, so you have a time-wise relationship. We'll come to that in a second when we have the diagrams. And then there's the most often fully asynchronous use case where you just, as I just put the example, you just insert an HDMI sender signal onto the network. You want to receive it some 100 meters away and put it out on on another screen in the next room or foyer or whatever. And you don't need any synchronization to any sort of signal at all, right? So that's these 3 use cases: fully synchronous, asynchronous but with a common reference clock, and the full asynchronous case where you don't have any media clock relationship. Let's state that IPMX at the moment defines all of these three operating modes as mandatory. So all the IPMX devices have to support these devices as it is right now defined by the standards. I know, I see your things, but you can you're right to add some words at the end. Important is, these 2 modes require a common reference clock on the network. That translates into PTP being available on the network. The 3rd mode is the one where you don't require PTP, because, well, there is no common reference. It's all asynchronous. No PTP is needed on the network. What's the PTP stuff of thing? PTP is the precision time protocol. It's an old-standing protocol, basically, originally released in 2002, revised in 2008, and it is yet another revision in 2000. Give me help, 22, 21, something like that. We are talking, when we talk PTP, about the 2008 revision, the PTP version 2 revision here. You can have a GPS reference or not, depending on the use case. It's a proven technology, not only used by us in the professional media world. It's measurement, military, instrumentation, whatever. So it's a really widely used protocol. It's not just invented or used for broadcast applications. And it's basically there to distribute time, to precisely distribute time to devices. It's not the media clock which is distributed, it's time. So we synchronize clocks with it. And it's important, both AES67 and 2110 are fully based on PTP as the common transport protocol for the common reference clock. Let's have a quick look at the first one, the fully synchronous operation. Well, basically that is identical to what AES67 defines. Let's have the case with the analog audio. The analog audio is coming into an A to D stage. The digital data gets packetized, and then a packet is sent out to the network. With AES67, the mandatory packet time is 1 millisecond, so we have 48 samples if we are doing 48 kilohertz in one packet, and it's shooting out to the network. Now, the A to D converter needs to be driven by a media clock, right? So that media clock, in turn, is driven or derived from a local clock, from a real time clock. So if you have time, you can translate that into a media clock. If you have time, you can derive any media clock you like. Let's say 48 kilohertz, that drives the AD converter. And that internal clock, in turn, is being synchronized via PTP from a common reference clock. That is the full synchronous use case for analog audio. If we move over to digital audio, it doesn't change much, except that the input source, the digital input source, is synchronized to that media clock. So either by a gen log or by a word clock signal or whatever, the external digital input device is synchronized, just as you know from the traditional traditional digital use case, right? You have lots of studio equipment, you're running a house clock around, that's the synchronization mechanism. And the devices have to follow that reference clock, and that's exactly what is output right here. So that's the full AES67 way of setup. And if you need to synchronize multiple devices to the very same time, you have a master clock in the system, is GPS referenced or not. PTP is distributed to the different devices, to the different clocks in the devices. And from there, we generate independently the media clock locally on every device. But since we have absolutely the same precise time, we have the same in-phase media clock running at all devices. That's the way how the media clock generation and distribution, which actually isn't a distribution, works. Then another important factor of the AES67 stuff is that we have a deterministic playout. Because we have time in the system, we can now tell every device when to play out particular samples, so that both speakers, or let's say an example like the Sphere in Las Vegas, which has 1,600 of these speakers, that they don't play out whenever they arrive a sample, but they play out at the very same sample align time. Otherwise, these systems just won't work. And that is managed through the link offset. Very quick and easy example, and thanks, Andrew, I stole that from your presentations. We have a sender which is generating packets at a quite isochronous way and emitting it to the network. All these packets have the origination timestamps with them, and our receiver, depending on where it sits on the network, might receive the packets at different times. And now it's the goal of a management system to align to the maximum required time to establish, to calculate the required link offset. And then by telling the receivers, okay, you all have to play incoming samples with this particular link offset with respect to the origination time, we have a perfect sample accurate alignment of the playout of all these streams. That's basically how every ST2110 and AES67 based infrastructure is working. The benefits, of course, all media clocks follow a common reference clock, and we have accurate reproduction of the reference clock at all local modes and identical or phase-accurate, even phase-accurate media clocks for all streams. We can concurrently process any incoming stream because they are all following the same media clock and they all have the time information. We have deterministic latency because the time information and any desired alignment is possible. We can even build, delay lines if we have live equipment and have front hanging bananas and the next one in the audience further back. We can build these delay lines for, no money at all. Basically, well, buffer inside the receiving devices, but it's not as expensive as dedicated devices here. The big drawback is we can't process and transport asynchronous signals. So all devices which participate in this network need to be synchronized to the common reference clock. Any asynchronous input signal needs to be sample rate converted before it actually is in line with all the other signals. So not just like, I have an HDM input, I can transport it with AES67 just over and receive it somewhere. I don't care about synchronization, not working. PTP is required, and some people consider, well, if PTP is required, we need a more complex setup then. Maybe true, it's sure more complex than without PTP, but what is complex? Anyway, that's certainly an aspect. Now let's look at the asynchronous operation mode where we have a common reference clock available. Again, we have the same picture here, and what we are omitting is the link between the clock and the media clock. So that means the media clock can either be free running, right, or could follow an externally provided clock. And with that media clock, the analog signal is digitized and packetized. Now, since we have a reference time, because we have PTP on the network, what we can do is we can provide information to anybody who wants to receive the streams when any particular sample has been gathered. Because we have a reference time, we have a media clock, which is running, and we can we won't do it at every clock cycle, but we can exactly measure, okay, what was the time when this sample has been gathered, what's the time when the next sample has been gathered, and so on. So we have a relationship between a common time known to everyone on the network and an individual free running or whatever media clock. So the receiver finally can resample the unknown media clock from the incoming information about what was the common reference clock time that particular period has been acquired, and what's the next one, and then I can reassemble the media clock. It can perfectly align the media clock from the input side. And that is done through the RTCP stream of packets. So in theory, it's not for every media clock cycle, but in theory, every media clock cycle has a timestamp. When was this clock cycle started? On the digital side of things, it looks different. We don't have that link anymore. But for the digital signal, that is now driving the media clock because it's already there. It's already digital. We packetize and still we build these RTCP combination. Media clock was at that particular reference time. So it's a very precise way of resample that media clock on the receiver side of things. Main benefits and drawbacks of this kind of operations scheme. We have any individual input clocking, so we are not forced to be synchronized to the whole network anymore. We have a deterministic latency because now we know it's been gathered at that particular point in time and we want to play it out after 2 milliseconds or 5 milliseconds or whatever. That can be achieved. We can precisely reassemble the digital input clock, really too. Wow, it's 10 minutes left. All right, and that is the fact. But what we can't do is in a concurrent processing of individual streams because they still follow their individual media clocks. We know when they have been gathered, but we can't process any 2 individual media clocks because usually we only have 1 media clock running per device, right? But we have the benefit of supporting asynchronous signals. This is exactly the scheme AVB, by the way, works. So AVB is exactly using this scheme of operation. Now, third case is fully asynchronous operation without a common reference clock. So what we lose is the reference. We still may have a local clock running, or we should basically, but now there is a more or less useless combination of the internal local clock and the media clock because the meaning of the local clock is not understood by the other devices on the network. We can do some tricky stuff with this, but in principle, that local clock does not have a relationship to any other local clock on the network anymore. So we still have the RTCP reports, If they can be made use of or not depends on certain circumstances. And for the digital side of things, it's pretty much the same. We have this digital signal feeding the media clock. We have the RTCP reports, and stuff is going out. Benefits, of course, I can now use any input signal. I don't need PTP on the network. Drawback, of course, I have always individual media series with individual media clocks. I can't do concurrent processing in one single device. And also, since I don't have any relationship to time anymore, I don't have any deterministic playout. I cannot work with any, I won't have that or this particular link offset anymore, because the time of the sender and the time of the receiver are different. But it's a very, very easy system setup because it's no PTP required there, right? Just input, output, done. So final question then is, I'll skip over this because that's the three operation modes which are resembled here. The PTP synchronous operation, PTP asynchronous operation, the generic operation when there's no PTP. We have a fourth case, which is not defined by IPMX, but that's when I feed an external house clock around and synchronize systems again, but I don't have that done via PTP. But it's not defined by IPMX. Now the final question really is, how do AES67 and IPMX work together? Can they work together? What are the constraints and limitations? General issues we see, AES67 always requires PTP. If there's no PTP, AES67 cannot work. AES67 devices don't support any asynchronous operation. So we always have to, for the interoperability, have to look at synchronous operation. Now, if you look into details, we can see that AES67 and 2110 also require higher clock accuracy for the GMs, for the grandmasters. So IPMX has a relaxed time specification for the accuracy, and that in turn has consequences for the capture range. That in turn may mean if you're having a GM which has the relaxed specification of IPMX, AES67 devices may not be able to capture a synchronously running stream. That's right, and so that's one of the details we probably would have to look further, but that's how it's standing at the moment. RTCP is a mandatory ingredient of IPMX. AES67 doesn't have that, but IPMX has defined that they need to operate in an AES67 mode, so the missing RTCP package should not pose a problem at all. And AES67 also doesn't specify any control means. IPMX does in turn. So no issues with the stream formats because what is defined in AES67 or 2110 conformance level A is also required for IPMX devices. SDP information is also basically the same mechanism, although IPMX is generating much more information, but AES67 devices need to tolerate this. Basically, if you add IPMX devices to an existing AES67 operation, we should not see any particular issues because IPMX devices are forced to lock to PTP if PTP is present. So we may see alignment timing issues depending on the clock implementation of the IPMX devices, but in principle it should work. So IPMX transmitting into such a network, only synchronous operation can work. We can't distribute any asynchronous streams. And the other way around, we don't find any issues. So any stream generated inside that stream should be receivable by IPMX. Vice versa, last slide. IPMX ST2110 AES6 device in an IPMX environment would only work if PTP is present and with a decent accuracy. And yeah, basically then we have the TX IPMX no issues, and the other way around, it's only synchronous flow which can work. In summary, I skipped that because it's just collecting this, and yeah, 6 minutes left. Any questions?